Okay, so we'll start by looking at the calendar. You can see there's not a whole lot left to the calendar. We're really getting to the end. Today we talk about power functions. Next class we talk about regression. And then on Friday and a week from today, the Monday, we'll review for the final. So we have 2 full days to review for the final exam because we didn't have a snow day. So that was what that was built in for. And so 1 week from today is the last day of classes for any class. And then our final exam is on May 16, which is Wednesday of next week. Any questions on any of that? Eric? It's 1 to 3. 1 to 3. Yeah. Other questions on the calendar? Okay, one bit of good news. As soon as people finish this quiz, then you will be finished with all of my quizzes. We had 10 so far. That was the last one. Okay, so on page 76, it talks a little bit about this new kind of creature called the power function. And hopefully in your reading, you guys did a little bit of work to try to figure out what these things are. So first, I actually collected a bunch of data from the males in the room. I have heights and weights, and we're going to use that data at the end of this class to do something. So we'll come back to that. Well, let's move on to number 2. Can we start with Sam? We'll go to Connor for recording. Okay, so this is our new formula right here. K times x to the p. That is called a power function. So you can go through the definition that Connor had read with the proportional business, but really just K times x to the p is our new formula for a power function. Can we go to Hazen for number 3? We're on page 76. Okay, so we're going to talk about the properties that power functions have in common. We're going to talk about why we care about power functions. First, we need to be able to recognize them before we can do any kind of analysis on them. So again, the main definition is underlined in red. K times x to the p. It either looks like that or it doesn't. If it can look like that, it's a power function. So let's take a look at 3x squared. Does it look like k times x to the p, a number times x to the number? Yes, it does. So is it a power function? Yes, it is. K, which is the number in the front, is 3. P, which is the power, is 2. That's why we call it P. It's the power. Good? That's a power function. You guys have seen power functions before because you know what 3x squared looks like. All right, how about this next one? 3x squared plus 7x plus 1. Does it look like k times x to the p? No. Nowhere in our definition do we have what important math symbol? A plus sign. There's no room inside of a power function for pluses. That's an imposter. Eric. Good question. Let's take a look at, I don't even have one. I don't know why I don't have one. An exponential function. It might be something like f of x equals 4 times 3 to the x. That's an exponential function. Where's the variable? It's in the exponent. That's what makes it an exponential function. For a power function, the variable is not upstairs. The variable is downstairs in the usual place. The power is the thing that changes. Okay, so big difference between 3x squared and 4 times 3 to the x. Again, you got to identify where that variable is to tell what you're looking at. Okay, so I guess what we're saying is that, what's the graph called for 3x squared? That's a parabola. You've seen it. What's the graph of this guy right here? That's a parabola. So is every parabola a power function? No. So I guess I can't just say every parabola is a power function. It might be, the first one is, but the second one is a perfectly good parabola, but it is not a power function. How about 4x to the 1.7? Is it a power function? Yes. So we can identify that the k is how much? It's 4, and the p is 1.7. Perfectly good power function. A number times x to a number. Let's take a look at part D. 5 over x squared. Does it look like a number times x to a power? Not at the moment. But that doesn't mean it couldn't be rearranged. Could you rewrite this? Let's see. I don't mind having the 5 there. I don't like that the x is on the bottom because there's no room in power functions for the x to be in the bottom. If I decide I want that x to be upstairs, Eric? Eric says x to the negative 2. Are they equal? 5x to the negative 2. Is that the same as 5 over x squared? 1 over x to the n. We've seen that, yes? It's the definition of a negative exponent. So having x squared on the bottom is the same as having x to the negative 2 on top. Is it a power function? Yes, it was the whole time. It just didn't look like the standard form. So sometimes you have to manipulate it a little bit to make it look like you expect power functions to look. How much is k? 5. How much is p? Negative 2. No problem that p is a negative number. It's perfectly legitimate. Okay, part E. 4 square root of x. Is it currently a number times x to a power? No, but we can make it. 4 square root. You know what power the square root is? It's a half. That's the same as the 4 square root of x. Is it a power function? Yes. Now we can recognize it, but it was a power function the whole time. We just didn't recognize it. So the k is 4, the p is 1/2. Yeah, last one has problems. But on part E, just one little thing. What kind of powers are now allowed? Yeah, we saw negative in part D. We saw fractions in part E. Fractions are fine. Doesn't say anything about it has to be a whole number. Just any constant. So negatives are good, fractions are good. In fact, I don't have one up here, but even worse than like your normal looking fractions, what if I had like 2x to the pi? Is that a power function? Yes, it's a constant times x to a constant. What does it even mean to take x and raise it to the pi power? I don't know, but it's a power function. Okay, the last one, 1 over 5x cubed minus 2, not a power function. Iris points out it's got subtraction. There's no room for subtraction in power functions. Okay, any questions on identifying power functions? Okay, so let's come down here to number 4. Okay, who's our reader now? We'll go to Serge for 4. Okay, so let's take a look at part A. We're trying to find, okay, so we'll evaluate those once we understand what x to the 1.7 is. Okay, this blue circle here tells me that I broke the smartboard, so we're going to come back and just use the whiteboard for a little while. But x to the 1.7, what could it possibly mean? Okay, I don't really know how to handle decimal powers. I can do fraction powers. Okay, all right, pause. You're going too quick. So can you guys write down, what is 1.7 as a fraction? Can you write go ahead, write it down. 1.7 as a fraction. Okay, what is 1.7 as a fraction? 17 over 10, agree? That's the reduced fraction for 1.7. Okay, so let's think about that. I'm trying to take x and raise it to the 1.7. which is really the same as x to the 17 over 10. Feels so weird to hold one of these. I'm not used to it anymore. X to the 17th tenths. You guys know that has to do with radicals. You can handle any fraction power by writing it as a radical. Okay, Iris, I'm going to ask you to raise your hand from now on because you're jumping too quick for me. Can you guys write down what radical that is? 17 tenths. I'll write a radical sign. I'll write an X. 17 goes somewhere. The 10 goes somewhere else. Do we remember where they go?
10 goes to the...
All right, it's the 10th root and x to the 17. This is what we know 17 tenths means, right? Maybe you've never seen 17 tenths, but that's what it means. Okay, I can deal with that. You take x, you raise it to the 17th power, great, and then you take the 10th root of it. It's a perfectly legitimate number, right? That's what x to the 1.7 means. You do those two things. Raise it to the 17, take the 10th root, you got your answer. Let's try a couple of these. No calculator initially. If I take 0 and stick it in there for x, how much is 0 to the 17? Is 0. What is the 10th root of 0? Also 0. So how much is that first one? It is 0. Okay, so f of 0 we decided is 0. Let's think about f of 1. 4 times, and then I'm going to write my definition there. We've got a 10th root of 1 to the 17. How much is 1 to the 17? 1. 10th root of 1 is 1. So the whole thing, 4. F of 1 is 4. Great. In fact, I feel like those 2 points are going to happen just like they did all the time. Did the 1.7 really come into play in either of these? Not really, because 0 to any power is 0. So I feel like for all of the power functions up above, f of 0 is going to be 0. Plug 0 in, you get 0 out all the time. So what that means is that the point 0, 0 is on the graph of all of these power functions. That is to say, they all go through the origin. Great. All right, why did we get a 4 out here? Well, 1 raised to the 1.7 was just 1, but 1 raised to anything is 1. So how come the answer was 4 here? Because that was the k, that was the number in the front, right? So then I feel like all the time it's going to be x equals 1, and the y coordinate is just going to be whatever the k is. In this case, it's 1 and 4, 1 comma 4. Okay, f of 26. Let's write down the definition. 4 10th root of 26 to the 17th power. Okay, 26 to the 17th is quite big. 10th root of it makes it smaller. How are we going to get a good approximation here? The calculator can handle that, no problem. Before we do, I want you to convince yourself that you actually can get a good approximation. Like, it looks crazy, but you can get a good approximation for this. Watch. If you do 4 times 26 to the 1.7, that's what we're doing, right? 4 times 26 to the 1.7. I'm going to compare that to two things. I'm going to try 4 times 26 to the 1, which is too small. And I'm also going to try 4 times 26 to the 2, which is too big. Having a little one at home, that too small, too big reminds me of like Goldilocks. And it's just, first one's too cold, last one's too hot. 1.7 is just right. Okay, 4 times 26 to the first. How much is 4 times 26? No calculators. Okay, so we got 104, that's too small. Okay, 26 squared, I don't know, minute 676. Maybe you happen to know that. Probably not. 4 times 676, about 4 times 700 is, okay, we'll see, roughly. Okay, the answer is going to be something between 100 and 2800, definitely. Which one do you think it'll be closer to, given the 1.7? All right, it's going to be closer, okay, 2000 something. Great, type it into the calculator now. I can type it in either way. So if you're really a glutton for punishment and you want to type in the thing that's blue, we could do the 4 and then the 10th root 4 times. Here's how we find the 10th root. We go into math and it's number 5. It's that x radical. And then what is it? 26 to the 17. So if you type all that stuff in, you'll get the right answer, 2000 something. So I would like us to be able to type in that 10th root. I mean, it's not one that we do very often, but it's easy to type in if you know where you're going. So you first type the 10, then you went into math and number 5. That's the x radical, which is any old radical. Okay, I don't know what the answer is. Are we close with our 2000 something? 2017. Okay, good enough. Okay, much easier than that is to type in what? 4 times 26 to the 1.7. You don't need to tell the calculator what 1.7 means. We needed to talk about what it meant, but calculator can handle it, and that's the way to type it in. Okay? All right, so when we're ready, we'll move on to the next page. So we've got about 1017 for this guy. Okay, and we're back around to Joe. Number 5. Okay, so we actually did these already, but if you plug 0 in for x, what are you going to get? Definitely going to get 0. If you plug 1 in for x, you'll get k. And so we talked about these 2 points, 0, 0, and 1, comma, k, all the time. As a quick example, if I think about the graph of y equals 4x squared, it's a very familiar one to us. What's the graph called? That's a parabola, right? So we got that guy right there. What point does it hit? Definitely hits the origin, right? We knew x squared hits the origin. Okay, now we see it's because it's a power function, it's always going to hit the origin. And if you plug 1 in, what do you get? Plug 1 into that guy, we get 4, don't we? We got this point over here, 1 and 4, along with the origin over there. If you made it 5x squared, what would happen to that point? Shift up, 1 comma 5. Okay, let's go to Ben for 7. Okay, so I'm just going to show you a real quick sketchpad thing here. The goal of what I'm about to show you is not to just memorize like all these properties, because I'm going to show it to you quick and I'm not going to test you on it, but I just want you to see we don't just name power functions so that I can give you another question on the quiz that says, is this a power function? But rather we name them because they have some properties in common. Like you guys know what the x squared family of functions looks like. You know how to take x squared and make it x squared plus 5. There's some commonalities there. There's commonalities here for these things named power functions. So all the time it's going to be kx to the p, same letters we've been using. At the moment, k is around 2 and p is 1. So this is really 2x to the first, 2x. Y equals 2x is the line. Great. Notice it hits what point? The origin. No surprise. It also hits that point, 1 comma 2. Probably it's too small to see that in the background, but 1 comma 2. Next thing I'm going to do is take this guy and drag it to the right. Now when I drag it to the right, it's going to go up by quarters every time. So the next one will be 1.25. Okay? X to the 1.25. Any idea what it looks like? Have you ever graphed x to the 1.25? I doubt it. X to the 1.25. I could give meaning to the 1.25 power by writing it as fraction. Somehow it's going to become 1.25, then 1.5, then 1.75, and then finally 2. When I get around to 2, can you guys show me with your hands? What will it look like when I do 2x to the 2? Okay, so that's going to be our parabola. We've seen that one. So somehow it's going to morph between the straight line here And a parabola, when I get up to x equals 2, what does it look like in between? All right, let's move this to the right. There's the graph of x to the 1.25. Is it still a straight line? No. Is it curvy enough to be the parabola yet? Yeah. Yeah, and something kind of funny happened over here on the right-hand side. I'm going to go to 1.5. Okay, I would say it's curvier. It's approaching our friend the parabola. I'll move it over to 1.75. There. And when we get to 2, magically that left-hand side blinks back into existence. Let's talk for a moment about why it disappeared. I'll go back to this 1.25. Can you guys write 1.25 as a fraction? 1.25 written as a fraction. What is it? So let's reduce. What do we get? 5/4. Okay, 5/4. Thinking of 5/4 as a fraction. If I have x to the 5/4, which one is the index? 5 or the 4? Which one goes in the front there? It's the 4, and that's an x to the 5th. That's a 4th root. What kind of numbers are bad inside of a 4th root? Negative numbers. If you plug a negative number into there, it's not real. Yes? 4th root of a negative number is not real. We tried plugging in all these negative x's here, blinked out of existence. It wasn't real. Disappeared. So I mean, there should be like some symmetric thing over here, but it dies because it's imaginaries. And then we do 1.5. 1.5 is a fraction. What is 1.5 as a fraction? 3/2. Which one of those numbers is the index? It's the 2, which means 3/2 as a power is a square root. Square root doesn't exist when you try plugging in the negative numbers. We can go to 1.75, same problem. It's another even power. Finally, when we get over here, we can move the thing. All right, let's do this. If we move it and finally get over to x squared, all of a sudden, we're back in existence on the left. There's no more radicals because it's exactly x squared. It's fine. If I keep going, 2.25, 2.5, 2.75, what does x cubed look like? Where's the left-hand side going to be when it pops back into existence for x cubed? It's going to be down, right? We know what x cubed looks like. So it comes back down there. And if we keep going, it comes back up there. You can see the graphs don't change much, right? I mean, it's a very subtle kind of thing. Like the graphs kind of all look the same. Notice they have been tethered the whole time to these 2 points which have dark circles on them. I'm going to increase k for a second. I'll make k 5. What happened to that point? Where's the new point up there? It's now at 1, 5. And just watch that point as I shift. Just keep your eye on that point 1, 5. The curve will change shape and start to gradually get to stuff that we've seen before. But what happened to that one point? Sat right there, said, you're going to come to me. I'm on the graph all the time. Okay, so that's when we do like quarters. How about we come here? This guy's going to go up by thirds. Instead of going up by 0.25 every time, it's going to go up by 0.3333 repeating. I want to think about what's going to happen before I pull that slider. The next power I'm going to give you guys is going to be x to the 1.3 repeating. 1.3 repeating is what fraction? It's 4/3, which means what's the index of the radical when it's 4/3? It's a cube root, and then it's to the 4th power. Does the cube root have the same issues with negative numbers inside of it? No, cube root exists all the time. So when I slide this thing to the right, we're not going to blink out of existence like we did before. When I go to 1.3 repeating, it's there. Looks kind of funny, but we have both parts. And then we move to the right, and we go up to 1.6 repeating. That one somehow went down below. And then when I get to the next one, I'll just get my familiar x squared, which is there. I'll keep sliding to the right. 2 1/3, 2 2/3, cubed. 3 1/3, 3 2/3, 4th. And so we get lots of stuff, again, tethered to the same 2 points and things that look quite similar to each other. And so that's, again, why we name this stuff, is because you can talk, like I could just, with a little bit of practice, I could ask you guys, okay, what does it look like if I graph this power function? And you just say, oh, is the one where they're both up or one's down, or does this one disappear? And you just figure it out. But they all kind of look like that. Now, there are some that look different. In fact, what power did we say was this guy here, that 4 radical x? What power was that? That's a 1/2 power. Can you guys trace in the air what the square root of x looks like when you graph it? What does it look like when you graph y equals the square root of x? I saw 3 people graphing. I want to see more. Square root of x, what does it look like? I'm still waiting for more hands. Do we not know what the square root of x looks like? Yeah. Yeah, okay, so I saw enough hands. Let's move on. So if we go here, I'll go back to this guy. If I want to make it square root, what power did we say? 0.5, right? 1/2. Okay, so we're going to take this guy. We used to slide up this way. Now we're going to slide the other way. There's a 0.75. There's the 0.5 you guys were talking about. That's a 0.25. It's a 4th root of x. Great. That looks quite similar to this guy, which is going to be in thirds. So we're going to get back to the first power, which is there. Next power we're going to show you is to the 2/3. It's there. It's interesting. And the 1/3 there, which doesn't look too far removed from this guy. It's just that this guy lost some stuff because you can't take the square root of a negative. Right? There's one other kind of power that we can talk about. What was the power on part D? It's a -2. Okay, negative powers. I'm just going to slide. We're not even going to really analyze. Let's do that one as fine. Okay, this power right here is a -0.25. There's a -0.5, -0.75. Looks quite similar. What point is on this one still? Still this 1,5, right? Is the other point still on it? No. Okay, I lied to you. I said the origin is always on it. Let's go back to this guy. Is the origin on this graph right here? What happens if you plug in x equals 0? It's undefined. Right, it's undefined. Okay, so I lied to you. If it's defined, the origin is on the graph. If not, then it doesn't hit the graph. We can keep going. Here's the -1st power. Again, all of a sudden we blink back into existence, but we're about to lose it. 1.25, 1.5, 1.75. There's to the -2 power. It comes back. And you can play the same game here with the thirds. Just this guy is not going to blink out of existence. It will always be there. And you can see sort of dancing things that look quite similar to each other. So we get these different kinds of things, whether you have like a fraction power, like a square root, negative power, this kind of thing, or positive power. But there's some commonalities there. Again, I'm not going to test you on it, just showing you. We name it because a lot of them look the same. Okay. Let's take a look at number 8. We'll go back to Katrina. Okay, for a lot of the graphs, the whole left-hand side disappeared, right? We had nothing out here for negative x's because we had all those square roots and 4th roots and all that stuff. Eric? Yeah, for most of these guys, the domain is going to be all the x's bigger than 0. Not all of them, but most of them. Because there's so many of those radicals. And you might think maybe it was just the special ones that disappeared, because I showed you some special ones. But even if I gave you something like this, x to the 3.4761, something like that. If you write this guy as a fraction, what do we get? 34761 divided by what number? Over 10,000? Yes? Okay. Maybe this thing reduces. I kind of doubt it, but maybe it does. But what's the radical? What's the index of this guy? This is the 10,000th root of something, right? 10,000th root. Does the 10,000th root have problems with the negatives, or is it okay? It has problems. You can't take the 10,000th root of a negative. Now maybe it cancels in just such a way that that 10,000 becomes an odd number, in which case all of a sudden we're okay. But how likely is it that you can cancel and that 10,000 will all of a sudden become an odd number? It just seems not very likely to me. Most of the time, it's just not going to exist because it's going to be an even radical. Okay, number 9, Brian. Okay, so you've got a bunch of data, and we're going to try to find a power function that hits all those points. First, we need our basic definition. What is our formula for power functions now? K times x to the p. Add that to your note card or your reference sheet or whatever. We need this formula. If on the final exam I say something about power functions, you're bringing this formula into it. Okay, let's first take a look at the first point, 0, 0. Is that comforting? Yeah. Is it helpful? No. We knew it was going to hit 0, 0 if it's a power function, probably. So thanks for nothing. Confirm something we already knew. Doesn't help you find K or P. Let's look at the next point, 1.5. That helps us quite a bit because we know that the point 1 comma K is on the graph, definitely. So how much is K? It's 0.5. I'm telling you, the Y value at 1, that's a gift. That's the value of K. Everybody see it? If I tell you what x is 1 corresponds to, you can grab it. That's the value of K. Okay, so our new formula updated. Instead of K, what did we just discover? It's 0.5. So it is now 0.5 x to the p, still p to be determined. Okay, we're going to pick another point. You can pick any old point. You might even pick the one with the nice numbers, the 8 and the 8. I'm going to pick the one with the not nice numbers. 2 and 1.26. What does it mean? Well, one of these guys is 2 and one of them is 1.26. Let's see. How much is the x? It's 2. So I got a 0.5 times 2 to the how much is p? I don't know yet. That's what I'm after. It's not on the table. Times 2 to the p equals how much is the f of x value at that point? Is 1.26. That's an equation I can solve for p. Where is the unknown in this equation? It's in the exponent. What technique do we use to solve when the unknown is in the exponent? We use logs. Okay. Do I take log right now? No. First, we need to get what out of the way? The 0.5. So let's divide both sides by 0.5. And then what do we do to both sides? Now we'll take a log. I'm not sure where to go. Maybe we'll squeeze this up here. 2.52 equals 2 to the p. So we're doing log on both sides. And what's the nice property on the right-hand side? I can take that p and move it right to the front. So I'll copy this guy and bring that p into the front. And then to solve for p, divide both sides by what? Log of 2. Okay, somebody with a calculator? Questions on finding P? This is a fairly standard test kind of question. I'd like you to be able to do this. Any questions on this one? Okay, so we'll just make sure we write our final answer. Turns out that for this one, f of x is equal to, what did we say k was? K was 0.5. X to the, what was p? 1.33. Probably it's 4/3. You know, the numbers in the table are rounded. So my guess is it's about 4/3. Okay, let's go to Tyler for number 10. Okay, k times m to the 2/3. What kind of a function is that? That's a power function. And here's an example where a power function comes up. If you know, you know, there's some value of k that applies to humans, and a different value of k applies to dogs, and different value of k for cats. So every animal has their own k. But if you know that value of k, then you can take the mass of one particular person or one particular dog, stick it into the formula, and all of a sudden you can tell what the surface area of the person or the dog is. Okay, I'm not super interested in that, but I'd imagine biologists are interested in stuff like that. So here's an example of a power function. Let's keep going with Sarah on 11. Okay, x to the 1.7. We have seen it before. What kind of a power function? Sorry, what kind of a function is that? That's a power function. And we know what it means. It has to do with the 10th root of something to the 17th. But if x is your height, and we know what k is, which is different for guys and girls, then we can predict what your weight will be. Now, of course, this is not an exact thing. We know there are a lot of factors that go into weight besides height. But let's see if we can use this, and then we'll take a look at the data that you guys gave me earlier today. So part A, Taylor. Okay, so here's our formula. K times x to the 1.7. That's the formula. Where do I put my 68? So it says x represents their height in inches. What is 68? X. 68 is the x. So I'm going to copy. K, I don't know. 68 to the 1.7, I'm going to type into the calculator in just a second. The left-hand side is the formula, F. What does F tell you? It predicts the average weight. That's what F is. It's your weight given your height. So what number goes over here on the left? 137. And that's enough information to find K. So K is 137 divided by 68 to the 1.7, whatever that magic number is. Okay, can somebody tell me about what K is? 0.105. That's the K for women, not just for this particular woman, but for all women. The value of K is 0.105. So we can now use this formula to estimate a woman's height based on, a woman's weight based on their height. So for example, if I tell you that I have a 70-inch tall woman, let's see if we can predict what the height sorry, what the weight is. Where do I put that 70? For the x, we go 0.105 times 70 to the 1.7. You can just type that in as it is. What do we get? About 144. Okay. So in theory, the average 70-inch tall woman will, on average, weigh 144 pounds. Doesn't mean that any particular 70-inch tall woman is going to be that weight. Like I said, there are a lot of factors that go into weight besides height. All right, can you guys with your neighbors try part B? First, we'll get Andy to read. Okay, check in with your neighbors. Same process as before. Okay, what's our prediction for the weight of our 66-inch tall man? 145? Good? Any questions on part B? Okay, so about 145 pounds there. All right, let's take a look at number 12. Eric? Okay, so I asked the gentleman in the room to share with me, if they were willing, their heights and their weights. So here are a few of the data points. I've typed them all into the calculator, and that's all that I did with that data. So first person, 71 inches tall, that's 5'11", 170 pounds. And then every guy in the room put their weight and height up here in inches, okay? First thing I'd like to do is see the graph of these things. So if I go into y equals, how do I tell the calculator that I want to see the dots? All right, so let's turn on plot 1. And then do you guys remember there's a nice way in here to tell it to find the dots once they're on? Yeah, we're looking for zoom stats, which is number 9. It won't find anything unless you put them on. Okay, what do you see here roughly? All right, the x-axis is height. The y-axis is weight. The taller somebody is, what do you see? The what? Heavier they are. That makes sense, right? As you go to the right, there's generally an increasing trend here. That makes sense. Is it an increasing straight line trend? Well, you know, it's hard to tell just from looking at a few dots, but according to what you guys just discovered, it's not a straight line that is supposed to hit those dots. It's the formula that we just found. What was it? It was 0.117. Is that the value of k that we ended up with? That's what it should be. Shouldn't be a straight line. It should be 0.117x to the 1.7. That's what it is for men. Okay, so the first thing I want to do is ask the calculator to graph that function, the quote right function. Okay, so 0.117, except I want to use the real number, so I stored that as k, so I'm just going to type it in as k. So alpha k, and then x to the 1.7. So this is the quote right formula, the average weight given an average height. Is it straight? No, you can see it curving up slightly. If I zoomed out a little bit, you'd see it curving even more than it looks like here. And what do we notice? Well, there are some guys who are pretty much perfect right on that curve. What does that mean? It means that their height and weight are the quote right relationship to each other. Okay, let's see if we can't find somebody who's on the curve. There we go. 69 inches, 155.8. That doesn't make sense. Okay, this is what I wanted to do. Sorry about that. All right, there's somebody. 67 inches, 150 pounds. How tall is 67 inches in feet and inches? 5'7". Yet another reason to abandon feet and inches. I had to think real hard to type in 5'7" as number of inches. Okay, if you're willing to share, if you are the guy who is 5'7" and 150 pounds, can you raise your hand? Ben has the correct height-weight relationship. Can we applaud Ben? All right. Okay, we've got that. Let's see if we can find somebody else. If you are willing to say that you are 6 feet, nope, sorry, 5'10" feet and inches. It's so dumb. Why do I have to think about what 70 means? All right, 5'10", 160 pounds. Who's that? Somebody who wishes to remain anonymous. That's fine, but congratulations, you're the right height and weight relationship. And then that's pretty good too. What is that? 5'6", 145. Would anybody like to receive applause for being the right height and weight? No, it's okay. We're shy, but well done. You know who you are. All right, so we've got our general trend. Now that's the quote right trend. That's the right formula. And you can see a lot of us are close to that line. Some people are below, some are above, but generally pretty close. Let's see if we can figure out what our class's formula is, because it's probably not that one. I bet we could find a better one to fit our data than this one. So here's how we're going to do it. We've done a lot of regression in this class. We did linear regression, quadratic regression, cubic regression. We find them all inside of stat. We scroll to the right. Number 4 is linear, 5 is quadratic, cubic, quartic. We looked at those. I don't think we've really gone below. But what do you guys think that means? Power regression. It is going to find the best power graph to hit as many of you guys as we can. So I'm going to hit A, and it's going to just do it on the normal data. But what do I have to tell it if I want it to graph the thing? To put it into the Y. All right, so I'm going to tell it to put it into Y. Now I'm going to tell it to put it into Y2 because I've already got something in Y1. Okay, 0.0166, that's the A value. We didn't call it A today. What did we call it? We called it K. 2.17, that's the B value. We didn't call it B. They called it P, that's the power. All right, so for the people in this room, the best power regression model is a 0.01667, that's smaller than the K that we got, and a 2.17 that's bigger than the P that we got. How is the R value? Not so good. That's okay. There's a lot of distribution, a lot of different height-weight relationships here. But I will tell you that of all the power graphs that we could find, that's the best looking one for the gentleman in this room. Okay, I'm going to go and trace and find somebody who's real close. Let's keep going until we get to, I want the guy at the far left. That guy. How tall is that? 5'4", 138, if you want to receive a round of applause. Hazen is the most average for the formula that you guys came up with, especially for the people in this room right here. Hazen at 5'4" and 138, can we, well done. The representative male in this class right here. And we'll just go ahead and turn this other one on as well, just so we can see the two of them together. You can see quite close to each other for a while, right? Our graph is generally a little bit higher than the quote right one, but quite close to each other. Okay. Any questions on any of that stuff? Would you like to show people where you are, Connor? Okay, so Connor is up there. What does it mean that Connor is way to the right? He's very tall. Connor is the tallest person in this room by a little bit. You just have to compare the horizontals between these two dots, right? And what does it mean that Connor is way up? He's the heaviest person in the room. Doesn't mean he's too heavy. It just, I mean, he's the tallest person in the room. I expect him to be the heaviest person in the room. So he is the heaviest person in the room. Not, you know, like there's the second heaviest person over there, and we can compare like weight differentials and stuff. Yeah, that's it. Okay, so at the risk of being accused of sexism, I did not ask the women in the room for their weights. I'm sure you understand why. I guess I'd rather be accused of sexism than asking a woman her weight. So I apologize if the women felt left out, but that was to sort of save my own skin. Okay, so one last thing here. The homework is actually not in the textbook for today or for tonight. The homework is right there. So when you're looking for the homework, it refers to this power functions handout, which is here, okay? All right, we have 1 day left of new stuff. Man, I'm just getting soft on you guys as we get closer to the end of the semester. 2.5 minutes before the end of class. We have one more class left of new stuff. Yeah, if you would do the homework on a sheet of paper and then turn it in as normal. Okay. All right. Have a wonderful day.